Okay, so thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Fatih Kaleoglu, who will tell us about simultaneous Haar indistinguishability and its applications to unclonable cryptography. So Fatih has a math degree from Princeton University, is currently a PhD student at UC Santa Barbara, where his advisor is Prabhanjan Anand. So his research is his main interest is in like cryptographic applications of unclonable and pseudorandom quantum objects. And in his free time, he likes to spend it with his family, with board games, nature, and music. So Fatih, the floor is yours.
Thank you very much, Kelo, for the introduction. Very honored to be invited to your seminar and give a talk. I don't know your usual format, but I'm happy to be interrupted with questions or happy to take them in the end. Either works for me.
Hmm.
Uh,
I think people will
so
normally interrupt.
yeah, I
Yeah,
prefer
yeah.
that.
Sort of
Okay.
semi-formal, informal kind of talk.
Yeah, that sounds good.
Mhm.
So this is joint work with my advisor Prabhanjan Ananth and Henry Yuan from Colombia. Um, so I will first give a summary of what we achieve in this work. Not everything might make sense immediately, but we'll go into detail throughout the talk. So our sort of main technical contribution is that we show an indistinguishability result between two distributions, uh, namely identical Haar random states and IID Haar random states. We show that if you have a non-local distinguisher that cannot communicate and could share an arbitrary amount of entanglement, if this distinguisher is given polynomially many copies from this one of these two distributions, it cannot tell which one it is. Uh, and we show that this has applications to unclonable cryptography. Uh, so the two applications listed here are very technically similar in nature. So we're only gonna delve into the first one in detail. But they are as follows. We show that unclonable encryption with indistinguishable security, which is the preferred security notion for unclonable encryption, is possible in the plain model if we allow the decryption keys to be quantum states. So previously, this was only known in the quantum random oracle model or other such limitations. Um, and in a similar vein, we show that single-decryptor encryption with identical challenge security exists in the plain model if we allow the ciphertext to be quantum. Um, so this one, we're not going to go into details. You can check the paper if you'd like, but there's a conceptual equivalence between these two notions, and it amounts to some sort of relabeling and looking at it from a different perspective. Um, so the proofs are very similar. And finally, in a different flavor, we show that there's a 2 out of n secret sharing scheme using quantum states uh, that has leakage resilience against arbitrarily entangled parties. So let's start. First, I'd like to talk about indistinguishability as a notion in cryptography. So typically, when we talk about indistinguishability, uh, we have a distinguisher D, and this distinguisher D could be a classical algorithm, it could be a quantum algorithm, uh, which we're more familiar with in our work, or it could be, as we'll study in this work, a collection of algorithms that have some restrictions of communication or entanglement amongst them. And the objects they're distinguishing, which I referred to as scenarios in the slide, um, could be, if you consider a simulation-based definition, they could be distinguishing some real world from some ideal world. Or in many cases, they could just be distinguishing some input distributions, classical or quantum. In this work, we consider sort of different input distributions of quantum states. So even though most people should be familiar with this expression, I list this here because it's going to be relevant. Usually the way we define indistinguishability is the probability of outputting, let's say, a fixed bit of 1 in both cases should be negligibly close. Now, you could also make an alternative definition, which in most cases would be equivalent to the previous one. And that is that if you pick randomly among two distributions, and if you ask the distinguisher to predict which one you chose, then the probability of success should be close to 1/2. This might be considered an unpredictability definition, but in the original, case of classical algorithms and classical distributions, the two expressions will be equivalent via an easy reduction. However, in our case of nonlocal adversaries and distinguishers, this is not necessarily true. So here by nonlocal, we mean two algorithms, Alice and Bob, that are spatially separated and they're going to be restricted in some way. So what's been considered in prior work is typically this LOCC setting, where they can perform local operations and they're allowed to communicate using classical communication. In this case, it still makes sense to consider the distinguisher outputting a single bit because it doesn't matter who outputs the bit, Alice or Bob, as they can communicate and agree on this bit before outputting the final bit. So in that sense, the two definitions will still be equivalent. But what we consider in this work is the setting where there is no classical communication. However, there could be shared entanglement. Now, it doesn't necessarily make sense to think about the same picture where they output a single bit because it's unclear who's going to output this bit. And in general, we can't force them to output the same bit. So we need to consider their collective output instead. So a better picture would look as the one on the right, where Alice is outputting some bit, Bob is outputting some other bit. And if we define unpredictability in this way, we would ask them both to predict the distribution correctly. And this has been considered in prior work. It's called, I think, simultaneous state discrimination. However, in this work, we'll consider the indistinguishability notion, which we listed first, where we just look at the probability that they output a fixed set of bits, let's say 0, 0, and we require that this probability should not change non-negligibly across the two distributions. Apologies for the typo. It should be row 0 and row 1 in the second expression. And in this setting, it also makes sense to consider multi-bit outputs because it's not immediate that it's equivalent to the single bit setting. So we can make the outputs.
I have a question. Could you go back a slide? Could you go back?
This one?
That second equation, both sides are the same.
Yes, so I apologize. The left side should be row 0.
Oh, okay.
Yeah. Sorry about the typo. So we require that this probability of outputting 0, 0 should be similar in the case of row 1 and row 0. Right, and we also want to consider the multi-bit output case in our setting. And in general, we would like the total variation distance to be close to 0, meaning the distinguisher can be modeled as follows. You give some bipartite state row as input to Alice and Bob. They are allowed to locally output some classical string of L bits. And then the distinguisher can take both of these strings and do some post-processing and then output some bit in the end. And then we can consider the indistinguishability definition as defined before. Right, so the reason we use the indistinguishability definition in our work is that it is more useful in that it has this transitivity property. So when we talk about indistinguishability, intuitively, we would like to see that if A and B are indistinguishable, B and C are indistinguishable, then this should imply, ideally, that A and C are also indistinguishable. So the unpredictability notion does not necessarily satisfy this, as far as I'm aware. But the indistinguishability definition does, because it's just the closeness of two probabilities, and you can use triangle inequality. And related to this, it becomes more useful in cryptographic security proofs, which use the hybrid technique. So this technique is also what we use in our unclonable encryption security proof. And so this particular choice of ours will come in handy. So now the question is what kind of quantum input distributions we should consider. So if the distribution, if the pair of distributions are such that, let's say Alice alone can distinguish them, then it's not really an interesting case, because you have no hope of sort of non-local indistinguishability that we want, because even one party alone can distinguish. So you could set Bob to always output 0, and then if Alice can distinguish, then collectively they also can. So the result of this argument is that the more interesting cases are when if you trace out one of the two parties, let's say if you trace out Bob, then Alice's local state should be the same in the two distributions given. So those are the cases that we're most interested in. And perhaps a very natural example of that, which we do solve in our work, is Haar random states. So sorry, there's a typo again. The second one should be row 1. The first distribution we consider is identical Haar random states, where Alice receives T copies of this Haar random state, and Bob also receives T copies. The second distribution is when Alice receives T copies of a Haar random state, and Bob receives T copies of an independent, different Haar random state. So now if you look at the local quantum states, it's identically distributed because it's just T copies of a Haar random state. But if you look at the global state, there's a large trace distance. If you're familiar with the symmetric subspace, there's a sort of global measurement that can easily distinguish between these two distributions with large advantage. However, if you don't allow global measurements, just local measurements that use pre-shared entanglement, and that's the question we're tackling in this work. So in general, we allow the adversaries to be computationally unbounded. So we don't use any computational assumptions in this result, even though they come up in the applications. We also allow them to pre-share an arbitrary amount of entanglement. But we restrict the number of copies to be at most polynomially large. And in this setting, we want to show that the distinguishing advantage is at most negligible. And I should also note that the sort of number of qubits that represent each Haar state is also polynomial. That's implicit here. So if there's no question about the problem statements, I will start talking about how to show this.
I just want to clarify. So when the measurement, so Alice, of course, is allowed to jointly measure her many copies.
Yes.
So that's sort of like the most complicated measurement that's allowed. But
yes,
you cannot have measurements across the two parties. Right?
Exactly. So Alice's input should be considered one state as a whole, and then Alice can perform any local measurement. In this case, it's T copies of a Haar state, so you can globally measure the T copies, but not the two T copies.
Okay. Okay, thanks.
Thanks for the question. Right. So when we talk about the proof, I'll try to convey the main ideas and refer you to the paper for the details, or I'll answer questions as asked. And we'll start with the simple case. I won't go into the details of the general case, but I'll highlight the main ideas. Okay. So the simple case, meaning T equals 1, so they each get one copy. So through a standard argument, we can assume that the two parties perform projective measurements. And the second assumption we have is that their pre-shared entanglement consists of EPR pairs. This might sound like a natural assumption, but in reality, we cannot show that this is without loss of generality. But for this presentation, I'll talk about this case. So in this particular case, the expression we want to bound looks like the middle expression on the slide. So the EPR pairs are shared between Alice and Bob. M is the projector of Alice, N is the projector of Bob. So the E's stand for taking the expectation over Haar distributions. So in one case, you take the expectation of two identical Haar states. In the other case, you take the expectation of two independent Haar states. So the second term is very easily the maximally mixed state because it's independent Haar states. But the first term will be the maximally mixed state of the symmetric subspace. Which means it's maximally mixed amongst bipartite states that are of this form, psi times psi. So using some technical expressions, identities of the symmetric subspace, we can show that this is very close to the bottom expression, where the swap is a swap operator that swaps the inputs of Alice and Bob. And D is the dimension of the Haar state. And this now, it turns out, is equal to 1/2 to the R D squared times trace of M times N partial transpose. And so there are two ways to verify this. One is just, writing out, expanding it. But that it's hard to discover this expression using that. So the way we discover this expression is using tensor networks. If you're not familiar, that's okay. But basically, it's a good way to sort of think about linear algebraic expressions that involve lots of variables. And so you make drawings for both sides, and then you shuffle the wires and see that they're equivalent. I recommend it as a technique if you work on these types of expressions. So yeah, I mean, once you are familiar with tensor networks, then this expression is easy to derive. If not, I don't think it's easy to derive, but it's possible to derive. And once you do that, then we can do a Cauchy-Schwarz inequality using the Hilbert-Schmidt inner product. And we use the fact that the Hilbert-Schmidt norm is not affected by the partial transpose operation. And the Hilbert-Schmidt norm is bounded by the dimension of the operator, the square root of the dimension. So we get 1 over d in the end if we perform the calculation. Because it's 2 to the r times d, the dimension of each register. And this bound is in fact tight asymptotically. You can just perform a simple attack such as measuring the first qubit and outputting it, and it gives you an advantage proportional to 1 over d. For the non-EPR case, you need to do something more complicated, which I'm not going to talk about, but some more linear algebraic manipulations, and the bound worsens to 1 over square root of d. If d is exponential, it still remains exponential. But we don't know if the square root of d is tight or not. So that's an open question. And for general T, the proof is quite similar. So previously, if we quickly go back to here, the way we obtain the swap expression is we write the mixed states of symmetric subspace as sum of permutations, of which there are only 2 in the case of T equals 1. The identity and the swap permutation. The identity one cancels out. For T copies, it's similar. The identity permutation will cancel out, but there are, I'm sorry, the product permutations will cancel out, but there are a lot more permutations left amongst the 2 T copies. So a key thing you need to do is you need to group these permutations based on how close they are to a product permutation. So how much they switch an Alice register with a Bob register. So if you group them based on that, that gives you the best bound. And we achieve a generalization of the T equals 1 case where the bound scales with T squared. But we also don't know if this T squared dependence is tight, although my gut feeling is that it should be. And yeah, that's the summary of our simultaneous Haar indistinguishability results. So I can stop for a second for questions here, and then I'll talk about why this is useful in the applications. Okay. So as I mentioned, it has applications to unclonable cryptography. And unclonable cryptography is quantum cryptography that leverages the fact that quantum states are unclonable in general. So one prominent or fundamental primitive is unclonable encryption, where it's an encryption scheme using quantum ciphertexts that are unclonable. So it is resilient to attacks such as, store and encrypt later type of attacks. And well, we don't know if it's possible in the plain model. We know through recent work that it's feasible in the quantum random oracle model. And people have considered some weaker security notions and such, but in its most basic form, we don't know that it's feasible in the plain model. And a common sort of problem with all the attacks or attempts against constructing it in the plain model is this identical challenge versus independent challenge problem, which I'll mention later. And yeah, let me go on the definition, and then I'll talk about what this is. So the ideal notion we want from an unclonable encryption scheme is sort of CPA style indistinguishable security. And the security game is as follows. It's going to be 3 phases. Now I'm going to switch the names a bit because it's a triplet of adversary. Alice is the cloner or splitter, and Bob and Charlie together will be a non-local adversary who can not communicate but share an entangled state. So what's going to happen is the adversary will pick 2 messages, M0 and M1, and then the referee will encrypt one of them at random and send it to Alice. Now, Alice has this ciphertext, which is this quantum state icon. And Alice's job is to try to clone this ciphertext. So it's going to create a bipartite state shared between Bob and Charlie. And this bipartite state could be entangled, that is allowed. And in the final verification phase, now Bob and Charlie, each of whom holds a supposed copy of the ciphertext, are going to be tested. So how do you test this? You give the secret key and ask them to decrypt and tell you which message was decrypted. So they each perform this task simultaneously. And if both of them succeed, then the adversary succeeds. And security says that the probability that they both guess the correct message is close to 1/2, which is the trivial probability when one party gets the ciphertext and the other party outputs a random bit. So this definition, in fact, is unpredictability based. It's not indistinguishability based. Unfortunately, people refer to it as sort of indistinguishable security, which I admit might be confusing. But in the proof, it's not great to use unpredictability based results if you do a sequence of hybrids. So the definition is unpredictability based, but in the hybrid technique, we need indistinguishability based tools to show security. So the way we construct this is using sort of the search to decision reduction concept from classical cryptography that uses inner products. And in particular, we're going to rely on the Goldreich-Levin reduction, search to decision reduction. So this has been tried previously. However, it runs into this identical challenge barrier. And the reason is that in the final phase, they both get the same classical decryption key. That's what we mean by identical challenge. Both parties get the same key. And then we don't know how to perform the Goldreich-Levin reduction. So to circumvent this issue, our key idea is to make the decryption key a superposition over different Goldreich-Levin samples. So the construction is as follows. The encryption key consists of a secret key K for a search secure unclonable encryption scheme, which means if you encrypt a random message, it's hard to output the exact same message in both copies. So it's a weaker notion. And so we have a random message X, random bit B prime. So what we do is we're going to sample a Haar random state, psi, and then we're going to sort of sample a Goldreich-Levin string R, but we're going to use the Haar state as that string. So it's going to be a superposition over different R's. And so the decryption key here is a quantum state. And the encryption will look like B prime XORed with M for a 1-bit message M, and encryption of X using the search secure scheme. Now, how do you decrypt? What you do is you first measure and collapse this quantum part of the decryption key, which gives you R and R.X XOR B prime. Now, using K, you can recover X through decrypting the ciphertext. And using now X and R, you can recover B prime. And once you have B prime, you can recover M. So it's a simple decryption procedure. I guess you could ask, if decryption just measures this state, then why did we use quantum in the first place? And the answer lies in the security proof. So what we want in the security proof is for Bob and Charlie to receive independent values of R. So if we just give them the same R and use a classical decryption key, then we don't know how to perform the search to decision reduction. And it has been tried, and nobody's been able to do it yet. But if it's a quantum superposition, then in some sense, effectively, they get independent Rs. Because if they were to measure both, then they're going to get independent R and R prime. So what we want to do is we want to use our simultaneous Haar indistinguishability to say that the security game reduces to the case of them getting independent values of R. So the red arrow represents here a reduction, which replaces sort of 2 copies of the same Haar state that are used to generate the decryption keys for Bob and Charlie, and replacing them with IID copies of Haar states. And when it's IID Haar states, it's distributed the same as just IID classical strings because it's maximally mixed. So the quantum key versus classical key, they're both the same when they're IID. Right. And because this is a hybrid step, we need the indistinguishability notion of Haar indistinguishability, not the unpredictability notion. And after doing this, now we can hope to perform the search to decision reduction using independent challenge Goldreich-Levin, which is already known in prior work. So that's wonderful. However, there's one more problem. If you look more closely to the game on the right here, where they receive independent samples of R, they not only receive R, but some extra bit. And So these bits are r.x XOR b prime and r prime.x XOR b prime for independent values of r and r prime. Because b prime is just a random bit, these are just random bits. However, they are correlated. In fact, if you XOR them, then it's the same as XORing r.x and r prime.x, which means it contains some information about x, the correlation between these bits given to Bob and Charlie, which means the type of Goldrake-Levin theorem we need looks as follows. So what we want is that if there's a non-local adversary, and when you give R to Bob, R prime to Charlie, in addition to these correlated bits, if they can output the correct inner product, r.x, and r prime.x, sorry, it's one more typo, hopefully the last one. So the white stickman Charlie here needs to output r prime.x. If there is such an adversary that wins this game on the left, and they can start with an arbitrary state, then what we want is we want to extract x from both of them. So if they win the left game with probability significantly larger than 1/2, we want them to win the just simply outputting x game. We want an extractor that can extract x from both with some non-negligible probability. So in prior work, this is known without the additional bit given to the parties. We know how to do this already. But it is some non-trivial step to show this for this correlated case. So I want to note that the identical challenge version of this game, where R and R prime are equal, it can be seen as sort of fully correlated Goldrake-Levin, where they have, bits of correlation as many as the length of R. So like n bits of correlation. And this is sort of Goldrake-Levin with only one bit of correlation. So even this requires a non-trivial proof, which also highlights the maybe conceptual difficulty of showing the identical challenge Goldrake-Levin theorem. Right, and so we make two observations. One is that the original extractor works even if Bob and Charlie are not only allowed to be both correct, but also allowed to be both incorrect. So with a weaker guarantee, the extractor still works. That's what we show. And then we perform a reduction that sort of goes from this to the game on the left we want. So the correlated bits kind of translate to the correlation of their final output bits, where they're both allowed to be wrong or both allowed to be correct. And that's all I would like to say about the proof at this presentation. And the reduction we perform is simple. The analysis is slightly more complicated, but it just samples these R's locally. And finally, so this concludes the part where I talk about application to unclonable cryptography. And I'll briefly mention the application to secret sharing. The idea is very simple. We would like to secret share a classical bit, B, amongst n quantum parties. And if the bit is 0, we give them copies of the same Haar random state. And we want to give them some maybe at least linear number of copies, or super log number of copies. If B equals 1, we give them IID Haar states, sort of T copies of IID Haar states. So there are going to be n different Haar states, and they get T copies each. And so now any one person cannot tell between B equals 0 and B equals 1 because the local quantum state is just T copies of a Haar state. However, if two parties come together, they can check whether their Haar states are identical by performing a swap test. And because they have T copies, the swap test will succeed with probability close to 1. So, because the advantage for single swap test is 1/2. If you have T copies, you can exponentially boost this to advantage close to 1. And so our simultaneous Haar indistinguishability says that even if there's leakage from all the parties, the sort of the two cases are still indistinguishable, B equals 0 and B equals 1, if there's classical leakage from all parties. Unfortunately, this leakage will be bounded in length, it's a bounded polynomial that's determined by the parameters of the construction. The reason is that I mentioned when I talked about Haar indistinguishability, we also consider multi-bit outputs. Our proof is for single-bit outputs, and the way we generalize to L bits of output is using a union bound, which gives an exponential dependence. So it's an open problem to improve that dependence, if at all possible. It's hopefully possible, I think. So that's why we can only get bounded amount of leakage at this moment. Right, let me summarize the results again. So we showed simultaneous Haar indistinguishability for polynomial copies of identical Haar versus independent Haar states against a distinguisher who cannot communicate but can share arbitrary entanglements. And we show that this implies nice results in unclonable cryptography, including the existence of unclonable encryption with quantum decryption keys in the plane model. Even though we allow additional quantumness, we still do have security in this identical challenge setting, even though the challenge is quantum. And in addition, we show a quantum secret sharing scheme for sharing classical bits with bounded leakage resilience. In the leakage resilience property, the parties can share arbitrary entanglements because it follows from our simultaneous Haar indistinguishability theorem. And with my final slide is I'll mention a few additional open problems that I haven't mentioned. Can we show simultaneous indistinguishability for distributions that are not the Haar distribution? So one thing I haven't mentioned in the presentation is, in a way, Haar indistinguishability is the easiest case of this. So any non-trivial such result would imply our result. It's a valid question to ask, can we show it for other distributions? And all our results are valid for arbitrary entanglements. So one can ask, does it matter how much entanglement the adversary has? Like maybe, it's secure against polynomial entanglements, but not secure against exponential entanglements. So are there such cases? And also, can we go one step further and resolve the sort of big open question of unclonable encryption feasibility in the plane model without changing the syntax and using classical decryption keys? And that's it. I can take questions. Thank you very much.
All right. Thank you for quite an informative talk. So we open the floor for questions. So if you have a question, please just unmute yourself. Maybe I can start with some of mine. Maybe it's sort of naive. So, like, how do these results change if, like, Alice and Bob say get different number of copies?
Oh, so you're saying Alice gets T copies, Bob gets T prime copies?
Yeah, I'm just curious. I don't know.
So
Perhaps it's not really an interesting version.
it doesn't matter because you can just take R bound for the maximum of the two, and you can consider that distinguisher as a special case. Let's say if T is larger than T prime, you can consider our result for T and consider
Oh,
that
okay.
distinguisher as a special case which ignores some of the copies.
I see. That's true. Yeah.
Yeah. But I mean, of course, this may not be the optimal bound, but it gives you a good
Mhm.
enough bound in most cases.
Yes. Yeah, I can see that. Right. Actually, I was curious about, like, so in the second open problem that you mentioned,
Uh-huh.
so do you have some idea of, like, how to find these kind of cases where you have this polynomial and exponential separation for the amount of entanglement?
Right. So actually, not really. I mean, we haven't explored this direction, but I mean, it's some it is surprising to me that our bounds don't care about entanglement at all. Uh, like for example, like in other areas of quantum cryptography, like in position verification, right? Like there are attacks with exponential entanglements
Mm.
against like any scheme, but like there's no attack with polynomial entanglement that is known to achieve the same thing, right? So in general, the amount of entanglement could be relevant, but uh, I don't know if it's relevant in this task of non-local distinguishing. So, but we haven't really explored this direction.
Okay. Mm. Mm.
Yeah, thank you for your talk. So I am not quite in this field, so I kind of ask very basic question. So I'm wondering, why do you consider this kind of a split case, like only entangled between Bob and Charlie, and Alice will send the entangled state to the Bob? Is this the normal consideration?
So are you talking about the unclonable encryption experiment?
Yes, yes.
So this one, right?
Yes.
So are you asking if this is like a standard type of security experiment?
Yes.
Yeah, so in unclonable cryptography, this is very standard, and here's the reason. So basically, what you do is you send the unclonable state. In this case, it's an unclonable ciphertext, but in general, in any kind of unclonable cryptographic primitive, the way you model unclonability is you take the unclonable state, send it to some Alice, whose job is to try to clone this, right? And what does it mean to clone? It means you can give it to two separate parties, and such that each party can have the functionality of this state. So in that sense, you're cloning the functionality of this state. You don't even have to get the exact same state, but you're cloning the functionality. So in the case of unclonable encryption, this functionality is being able to recover the message using the secret key. So that's the functionality of the ciphertext. And if you have unclonable security, that means one of the parties cannot do this because they cannot have the ciphertext, like both of them at the same time, because the state is unclonable. But there are other examples in unclonable cryptography. Like if this was a quantum money scheme, then we would have a similar game, but we would ask each party to pass some quantum verification using their supposed money state. Or if it's copy protection of some functionality, we would, so in this verifications phase with the referee, we would ask each of them to evaluate the function on some input, secret function on some input. So whatever the functionality of the unclonable state is, the security game looks similar with, like you can change the verification protocol, you can change the initial state given, but the general template looks like this. And we have a work with Prabhanjan and Chipang that's called Cloning Games, that kind of talks about this conceptual framework that ties all these unclonable crypto primitives together. So feel free to check that out if you're interested in this sort of common structure.
Okay, thank you very much. And so another basic question, what's what do you mean by locally sampling R and R prime when you are talking about there are some sampling?
Yeah, so there I very briefly mentioned it because I didn't have time to go into details. I believe you're referring to this slide. So what we mean is there's a reduction where you only get R and R prime as input. So the original extractor works for a game where you only get R and R prime as inputs. This should be R prime. Yes. So you only get R and R prime as input and not this extra bit, right? So in that reduction, you're gonna sample, so you're gonna sample this bit. Oh, sorry, I think I misspoke. You're very, very right to be confused because I misspoke here. It's not even R and R prime. What you do is you locally sample these bits randomly. So that reduction is from this to a game where you don't have these bits. And then the reduction samples these just randomly. So Bob is going to sample his own local random bits for this, and Charlie is going to sample another independent random bit. And then because of the weaker guarantee, we allow them to be both incorrect. Then the reduction goes through some probabilistic analysis. So yeah, I apologize, I misspoke here. They locally sample this correlated bits. So they sample it in an independent way, of course, and that comes at the cost of, weakening the guarantee of the outputs. So in this game, they're required to both output correctly, but the reduction has the guarantee that they're either both correct or both incorrect. So you sacrifice some guarantee, but you don't need a correlated bit in return. You can sample sort of locally uncorrelated bits. So that's what I mean.
Okay, I see. Okay, thank you very much.
You're welcome.